Hi, this video covers Lesson 4 for Unit 4 in Chemistry. In this lesson, we'll be talking about Boyle's Law as well as the Combined Gas Law. For our lesson objective, students will understand the relationship between pressure and volume as well as the relationship between pressure, volume, and temperature.
So we're going to begin with Boyle's Law. Boyle's Law states that at constant temperature, the pressure of a gas varies inversely as the volume of a gas. That means that if the pressure increases, the volume will decrease, it'll go down, and vice versa. In the formula you see at the bottom of the slide, we have P1 times V1 is equal to P2 times V2. The P here is pressure in any pressure unit, including ATM, mmHg, PSI, and the V is volume in any volume unit, including liters, milliliters, centimeters cubed, and so on. The applications of Boyle's Law, well, there's many. On the picture on the left, you see a paint can being used, and there's propellant inside of the paint can that puts pressure on the container and goes ahead and propels the paint to go out. For the syringe, it works with the same principle, Boyle's Law, where if you pull back on the plunger, that's going to go ahead and allow the pressure from the atmosphere to pull in a liquid into the syringe. If you ever open a can that's been stirred, then again, Boyle's Law applies where you have a change in pressure and will allow the gas to expand very quickly, and you might get sprayed with soda. The picture on the top right, that is of a pressure chamber used if someone has the bends. That's a situation where someone, perhaps they were scuba diving and they dive to the bottom much too quickly, or maybe they go from the bottom to the surface much too quickly. Their body doesn't have the time to adjust, and what that begins to happen is they develop bubbles inside their blood, air bubbles, and that is extremely painful, could be even fatal. So what they do is they put the person into the pressure chamber and then slowly begin to acclimate that person to the outside pressure of the room. Now let's go ahead and take a look at some examples.
In example 1, we're asked the following question. A gas has a volume of 2 liters and a pressure of 1 atm. What volume will the gas have at 4 atm? We're going to assume that the temperature remains constant, so it does not change. We're going to go ahead and use Boyle's Law to go ahead and solve for this problem. That is, P1 times V1 equals P2 times V2. Remember, this is your before and after. When you read the question, usually the first sentence will give you your before, P1, V1, and the second sentence will give you the after. So it says a gas has a volume of 2 liters. There's our volume at a pressure of 1 atm. So let's substitute those values in. 1 atm for the pressure, 2 liters for the volume. Then the second part, they ask, what volume will the gas have at 4 atm? So that's our P2, 4 atm. And the question is, what will be the volume? Alright, so now that we have the numbers in, we can go ahead and solve for the V2. All that we got to do is go ahead and divide both sides by 4 atm, so that way we can go ahead and isolate the V2. So I'm going to go ahead and do that. 4 atm, 4 atm, that will cancel out that, giving us V2 all by itself. And in this side, we're going to go ahead and multiply 1 times 2 divided by 4. That's going to give us 0.5 liters. That will be the volume of the gas after the pressure increases from 1 atm to 4 atm. That takes care of example 1. Let's go ahead and move along to example 2. In this one, it asks, a gas has a volume of 50 milliliters and a pressure of 8 psi. What volume will the gas have at 10 psi? Again, assume that the temperature remains constant. Alright, so let's go ahead and once again use Boyle's Law. And in Boyle's Law, the units are not important. The fact that they gave us psi, we do not have to convert them to atm or any other unit. We can go ahead and use the units that were given to us. Alright, so we have 8 psi as our pressure, initial pressure. So that is our P1, and that initial volume is 50 milliliters. Now they go ahead and they give you a new pressure of 10 psi, so we're increasing the pressure from 8 psi to 10 psi, so that will be P2. And once again they ask you, solve for the volume. What will be the new volume of the gas if we increase the pressure from 8 to 10 psi? So we want to isolate V2, that means get rid of the 10. So to get rid of the 10 psi, we're going to go ahead and divide it by itself. And what I do to one side, I have to do to the other. So that cancels out. So it gives V2 is equal to 8 times 50 divided by 10. So that's going to go ahead and give us a volume of 40 milliliters. And that is our answer for example number 2. Now, example 3, they asked us the following. It says a gas has a volume of 20 liters and a pressure of 5 kPa. What pressure will the gas have at 25 liters? So now our new volume, we're changing the volume from 20 liters to 25 liters. So what do we have to do to the pressure to go ahead and obtain that change in volume for the gas? So let's go ahead and solve this problem. Alright, so the gas has a volume of 20 milliliters, and I'll plug that in at a 5 kPa, so that's kilopascals, so 5 kPa for its initial pressure, and 20 liters for the initial volume. Next, what pressure, so we're solving for P2 in this instant, will the gas have if the volume changes to 25 liters? Alright, again, our goal is to solve for the pressure, so we want to isolate it. That means get rid of the 25. So same type of problem where we just got to divide by the number next to the unit we're solving for. And I'll cancel out. So it'll be 5 times 20 divided by 25. That's going to go ahead and give us 4. 4 kPa is what the new pressure needs to be to change the volume of the gas. That is our answer for example 3. In example 4, they say the following. A gas has a volume of 3 milliliters and a pressure of 2 atm. What pressure will the gas have at 24 milliliters? Alright, so similar to example 3, and let's go ahead and solve it. So we have a pressure of 2 atm initially, and 3 milliliters. So we want to know at what pressure, so P2 is what we're solving for, what pressure will the gas have a volume of 24 milliliters? Alright, so I want to isolate P2, so I'm going to get rid of the 24, so I'm going to divide by 24 milliliters on both sides. Isolating the P2, so it's going to be 2 times 3 divided by 24. So it's going to go ahead and give us 0.25 atm. And that takes care of example number 4.
Up next is a combined gas law. The combined gas law, that puts together Boyles Law and Charles' Law. So we can have P1 V1 over T1 equals P2 V2 over T2. P means pressure in, again, any pressure unit, ATM, PSI, kPa. V is volume in any volume unit, liters, milliliters, centiliters. But T is temperature. It's got to be in Kelvin. All right, so if it's in Celsius or Fahrenheit, you've got to change it to Kelvin. How do you change to Kelvin? At the bottom of the slide, you see the formula. If you get your temperature in Celsius and you add 273, and that gives you your temperature in Kelvin. Now let's go ahead and take a look at some examples.
In example 5, we're asked, a gas at 2 atm and 27 degrees Celsius fills a flexible container with an initial volume of 3 liters. If the temperature is raised to 127 degrees Celsius and the pressure is increased to 4 atm, what is the new volume? So we got 3 things at play here. We got volume, temperature, and pressure. So we're going to go ahead and use a combined gas law formula, here it is, to go ahead and solve for this new volume. So we're going to begin by first writing down all the data that we have where it belongs. So the first sentence usually has our left side of the formula or before P1, V1, and T1. So it says a gas has a pressure of 2 atm. So there we go. So I'm going to go 2 atm here. And 27 degrees Celsius for the temperature. And the volume is 3 liters. All right, so that all came out of the first sentence. The second sentence usually has the after. So that's P2, V2, or T2. So if the temperature is raised to 127 degrees Celsius and the pressure is increased to 4 atm, what will be the new volume for this gas? So there we have it. Those are all information that's given to us. So P1, V1, and T1 are before will go here on the left. P2, V2, and T2 will go here on the right hand side. Now we're missing for V2 the new volume. I also wanted to go ahead and point out the fact that their temperatures, they are in Celsius, and they cannot go in Celsius into the formula for the combined gas law. They must be in Kelvin. So to change Celsius to Kelvin, you get the Celsius temperature and now 273. So we're going to go ahead and do that to each one of these before we plug them in. So it's going to be 27 degrees Celsius plus 273. That gives us 300 Kelvin. So that's really this value right there. And for the 127 degrees Celsius, same thing. We're going to go ahead and add 273 to change it from Celsius to Kelvin. So it's going to give us 400 Kelvin. Alright, so now I've got the correct values. I'm going to plug them into this formula. So initial pressure was 2 atm. And initial volume was 3 liters. Over a temperature of 27 degrees Celsius, who we've corrected to be in Kelvin, 300 Kelvin. Next, I'm going to go ahead and do the right-hand side. So that's going to be 4 atm multiplied times V2. We don't have that value. That's actually what we're solving for. Divided by the temperature, which was 127, but we changed it to Kelvin, 400 Kelvin. So there we have it. There's the initial setup. What we're going to go ahead and do now is we're going to try to isolate V2. So we're going to do a little bit of cross multiplication to go ahead and try to isolate V2. So it's going to be V2 multiplied times 4 multiplied times 300. That's going to give us V2 times 1200. And it's going to be 2 times 3 is 6 times 400. It's going to give me 2400 on the right hand side. Next, again, our goal is to isolate the V2. So we want to go ahead and get rid of the 1200. So I'm going to divide both sides of the formula by 1200. So our answer, it is 2 liters. That is our final answer. So the volume changed from 3 liters down to 2 liters after we changed the temperature and the pressure. That is example number 5. Let's go ahead and move along now to example number 6. Number 6, you ask a similar question. It says a helium-filled balloon at sea level has a volume of 2 liters at 10 psi and 27 degrees Celsius. If it is released and rises to an elevation which the pressure is only 5 psi and the temperature is 225 Kelvin, what is the new volume of this balloon? So let's go ahead and solve for that. Alright, a couple of things I wanted to point out. Number 1, this temperature is already in Kelvin, so we don't have to change to Kelvin, but this original temperature that was given to us, 27 degrees Celsius, is in Celsius. That does have to be changed to Kelvin. So 27 plus 273, that gives us 300 Kelvin. So our T1 is 300 Kelvin. So the helium-filled balloon is at sea level and has a volume of 2 milliliters and a pressure of 10 psi. And next, they go ahead and they change the pressure to 5 psi. And the new temperature is 225 K. So I want to know what will happen to the volume. We're decreasing the pressure and we're also decreasing the temperature from 300 down to 225 and from 10 psi to 5 psi. Alright, so let's go ahead and plug in these values into the formula and go ahead and solve. So it's going to be 10 psi multiplied times 2 milliliters over the temperature of 300 Kelvin. It's equal to 5 psi multiplied times V2, that's what we're solving for, divided by the new temperature of 225 Kelvin. Alright, so now we have this problem set up. Our initial step for solving for this is just going to be to cross multiply in an attempt to isolate the V2. So we're going to go ahead and cross multiply on this. That's going to be V2 times 5 times 300. That's going to give us V2 times 1500. On the other side, it's going to be 10 times 2 times 225. That's going to give us 4500. Next, I want to isolate the V2, so I want to get rid of the 1500. So I divide both sides by 1500. That cancels out, so therefore V2 is 4500 divided by 1500, which gives me an answer of 3 milliliters. Alright, that takes care of example number 6. Let's go ahead and move on to example number 7. Example number 7 says, at 200 Kelvin and 1 atm pressure, a sample of gas occupies a volume of 30 milliliters. If the temperature is increased to 300 Kelvin and the entire gas sample is transferred to a 20 milliliter container, what will be the gas pressure inside the container? Alright, so let's go ahead and write down all the given information to us. Initial pressure, volume, and temperature. It says at 200 Kelvin, so that's our temperature. And 1 atm. The sample occupies 30 milliliters. Next sentence says, if the temperature is increased to 300 Kelvin, and we transfer it from the 30 milliliter container to a 20 milliliter container, what will be the pressure inside of that container? Alright, so let's go ahead and plug in these values into the combined gas law and solve for this. So we have 1 atm for the initial pressure, P1. V1 is 30 milliliters divided by the initial temperature of 200 Kelvin, and that equals P2, which is what we're solving for. What would be the new pressure multiplied times 20 milliliters divided by 300 Kelvin, which is the new temperature. Our goal is to isolate that P2, so we're going to go ahead and cross multiply 20 times P2 times 200. That's going to go ahead and give us 4,000 times P2. And cross multiply here again, 1 times 30 times 300. That's going to go ahead and give us 9,000. Alright, so we finished the cross multiplication. What's next for us? We're going to go ahead and divide by 4,000 so that we can isolate the P2. And that's going to go ahead and give us the following answer for the pressure. So it's going to be 9,000 divided by 4,000. It is 2.25 atm. That will be the new pressure for this container. Alright, that takes care of example 7. Let's move along to example 8. In example 8 it says the following. A sample of air in a syringe exerts a pressure of 100 kPa at a temperature of 27 degrees Celsius. The syringe is placed in a warm water bath at 87 degrees Celsius. The pressure in the air is increased to 120 kPa by pushing the plunger in, which reduces the volume to 0.2 milliliters. What was the original volume of the air inside the syringe? Alright, so this time, going a little bit backwards, we're going to be solving for V1. So let's go ahead and do that. So let's get all of our initial information. So it says it was 100 kPa for our original pressure at a temperature of 27 degrees Celsius. Of course, we're not going to use that value, right, because it's in Celsius. We need it in Kelvin. So to change it from Celsius to Kelvin, we add 273. So 27 plus 273, that gives us 300 Kelvin. That's the temperature we will use. Next, the second sentence starts by saying the syringe is placed in a warm water bath at 87 degrees Celsius. So that's our new temperature. And the pressure of the air is increased to 120 kPa when they push the plunger into the syringe. And they want to know, and then that will change the volume to 0.2 milliliters. So what was our original volume? Alright, before we start plugging in numbers, we need to change that 87, and we're going to add 273. That's going to go ahead and give us, in Kelvin, 360 Kelvin. Now that our temperatures are in Kelvin, we can go ahead and plug them in and solve for the original volume. So let's go ahead and plug in. So we had 100 kPa, so that's P1. V1 we do not have, that's what we're solving for. And our T1 was 300 Kelvin. On the other side we have 120 kPa, that's our new pressure after the plunger was pushed in. And the volume was 0.2 milliliters, and our temperature was 360 Kelvin after the syringe was placed in a warm water bath. Alright, so there's our setup. We're solving for V2. the work we're going to do is much like the other ones, where we're just going to cross multiply and then try to isolate the V2. So let's go ahead and do that. So it's going to be 0.2 multiplied times 120 multiplied times 300, and that gives us 7,200. On the other side, it's going to be 100 times V1 times 3,600, so that will give us 36,000. Alright, so that's the product of our cross multiplication. Next, we want to go ahead and isolate V1, so we're going to go ahead and divide by the number next to it, so we can go ahead and have the V1 all isolated, which is 36,000. So we divide both sides by 36,000. So 7,200 divided by 36,000 gives us a volume of 0.2. Let me double check that. 0.2 milliliters. I double checked that because I just noticed that is the same value. And yeah, it happens, although we increase the pressure, and increasing the pressure reduces the volume of the gas, we increase the temperature, and that expands the volume of the gas. And so they ended up balancing each other out, and we ended up with the same volume that we started with. So that's the answer for number 8. Let's go ahead and move along to example 9. In example 9, they ask you as the following. An unopened, cold 2-liter bottle of soda contains 46 milliliters of gas, confined at a pressure of 1.3 atm at a temperature of 5 degrees Celsius. If the bottle is dropped into a lake and sinks to a depth at which the pressure is 1.52 atm and the temperature is 2.09 degrees Celsius, what will be the volume of the gas in the bottle? Alright, so let's go ahead and solve this problem. So let's go ahead and write down everything we do know. Now, the bottle is a 2-liter bottle of soda, but that's going to be irrelevant. What we care about really is the gas, because the water, well, the soda is a liquid, and liquids do not get compressed, but the gas is. So it is the volume of the gas that we're interested in here, which is 46 milliliters. Okay, now this is at a pressure of 1.3 atm and a temperature of 5 degrees Celsius. So that's the information that's given to us. Next, they go ahead and you drop it. As it sinks to the bottom, there's more pressure at the bottom. So it goes from 1.3 to 1.52 atm. And a temperature, it gets colder, of 2.09 degrees Celsius. And they want to know what is the volume of our gas. Alright, so for the 2-liter bottle, there will still be 2 liters of soda, because again, a liquid hardly ever gets compressed at all. So we're going to ignore that number. Alright, so that's all the data that we have, and that's everything that we need. First of all, we need to change these guys to Kelvin. So 5 plus 273 will give it 278 Kelvin. And this one's going to be 2.09 plus 273 is going to go ahead and give us 275.09 Kelvin. Alright, so now we have all our values, we can go ahead and plug them into the combined gas law right here. And let's go ahead and do that. 1.3 atm multiplied times 46 milliliters over 278 Kelvin. It's equal to 1.52 atm times V2, which is what we're looking for, over 275.09 Kelvin. Alright, from here we're going to go ahead and cross multiply. So it's going to be V2 times 1.52 times 278. So it's going to give me V2 times 422.56. And that's going to equal, on the other side, 1.3 times 46 multiplied times 275.09, and that gives me a value of 16,450.4. I'm going to round that off slightly a bit. Now I want to isolate the V2, so I'm going to go ahead and divide by the 422, so that way I can get rid of it and isolate the V2. So I'm going to go ahead and do that, and what I do to one side, I do to the other, just like in your math class. So that's gone. V2 equals 38.93 milliliters. And that is your answer for number 9. Alright, let's go ahead and move along to our last problem. This is going to be number 10. And in 10 they ask you is, what will happen to the volume of the gas if the pressure is cut in half and the temperature is doubled? Alright, so what will happen to the volume of the gas if we just go ahead and do those things? So let's go ahead and solve this problem. Now this is example problems where you don't really have anything to work with. There's no numbers there, but you can plug in your own numbers to go ahead and solve for this type of problem. Alright, so for example, I'm going to start with an initial volume of 1 liter so that it's easy to compare what will be the new volume. Alright, now what happened to the pressure? The pressure is cut in half. So make up a number and then cut it in half. For example, I'm going to say the initial pressure was 10 atm, so now I'm going to cut it in half. That's going to be 5 atm. Alright, and the temperature is doubled. Alright, so come up with a number. Let's say that the initial pressure was, let's go with 100 Kelvin. And what we're going to do, we're going to double the temperature. So it's maybe 200 Kelvin. So there, I've made up the numbers, but notice I followed their recipe where it said double the temperature, so I did, and cut the pressure in half. Alright, and our initial volume, you always put a 1 for the initial volume, and that's going to tell you, if you get a 0.5, you say, well, the volume is now half of the original. If you get a 2 or a 3 or 4, you can say it's twice as much, or 3 times as much, 4 times as much as the original. So that's what we're going to go with. Let's plug in our made up numbers. So it's going to be 10 atm times 1 liter over 100 Kelvin. That's going to go ahead equal 5 atm times V2 over 200 Kelvin. Alright, we're going to go ahead and cross multiply so we can isolate the V2. So we're going to V2 multiplied times 5 multiplied times 100. So it's going to be V2 times 500, and that equals 10 times 1 times 200. So it's going to go ahead and give me 2,000. Alright, next I want to isolate the V2. So I divide by 500 on both sides, so that way they can cancel out, giving me the V2 all isolated, and it's going to be 2,000 divided by 500. It's going to go ahead and give us 4 liters. Alright, so the volume went from 1 liter to 4 liters, so that is 4 times faster. Or, I'm sorry, 4 times larger. Alright, that takes care of example 10. This also brings us to the end of our lesson, and thank you so much for watching.